I'm Jay Bishop, and this is my project for Jeff Clune's Artificial Intelligence course at the University of Wyoming. My project uses the arcade learning environment, built off the Stella Atari 2600 emulator. I chose the game Seaquest for my project, and set out with three main goals to achieve. The first goal was to create a tree of game states, and to evaluate them based off of in-game score. The second was then to come up with a better way to evaluate those intermediate states in the tree using an evaluation function. And then the last goal was to make an environment stochastic and choose actions based off of their expected payoff. Creating the tree using ALE required saving a game state, having our submarine take an action, thus entering a new game state, getting that state's reward, and then loading the state we saved. Using this, one is able to create a tree of game states, and then search that tree to find the ideal next action. With this tree of game states, and taking actions that produce the highest possible scores, we get the following average scores based off the depth of our tree. Two issues, however, arise with this current setup. One is that the ship takes only actions that maximize its in-game score, randomly choosing a move if there is no clear better action to take. The ship does not factor in elements such as oxygen or lives, which can be seen in this run where the submarine kills itself. The other issue with this setup is time. Now, it may be tempting to increase score by simply increasing the depth of our tree. However, due to our use of depth-first search, this would drastically increase the time it takes our bot to run. With a branching factor of around 5, being the 5 actions our submarine can take, increasing the depth of our tree by just 1 increases the time it takes for our bot to run by a factor of 5. To solve this issue, I create a function that evaluates states based off of more than just their in-game score. I used the ALE to get screen data for each state and scan through that data to get important game information, taking into account things such as current oxygen with relation to ship depth, the number of divers in our hold, current lives, and the proximity of enemies to increase total average score without increasing our tree depth. This graph shows off how this function was able to triple average game score at each depth without hurting us in terms of time complexity, allowing our bot to stay low and avoid enemies, and then ascend when it has low oxygen and at least one diver in its hold. Although this function did improve results, I decided not to stop there. Having a fully observable, deterministic environment felt a bit dull to me, so I decided to use the new ALE ActionRepeatStochastically parameter to make my environment stochastic by giving all of my actions a 25% chance of repeating without my say for the next frame of the game. With this parameter set to just 25%, my bot's scores took a huge hit and ceased to get better when adding depth to my tree. This is due to us choosing actions based off of ideal rewards, but neglecting the fact that we only have a 75% chance of successfully doing that action. Instead, we need to try and maximize our expected payoff by factoring in the chance that we may end up in a non-ideal state. For example, in this particular situation, it makes the most sense to have our submarine move up and then fire to kill the shark. However, there is a 25% chance with the stochastic repeat that it will instead move up twice, resulting in death. For this reason, we need to also take into account the chance of entering a different state than the one we expect. To accomplish this, we take the reward we would be given if we enter the state we expect to enter and multiply that by 0.75, or the chance of entering that state. Then, we add in the reward we would get if the action repeat stochastically triggers and we go into a different state, multiplied by 0.25. This helps us predict expected payoff of a state and helps us stay away from dangerous moves that could hurt us if the random repeat occurs. Doing this, I was able to increase my average scores to just under what they were before the stochastic repeat was added in. With this, my final goal was met, meaning that I was able to, with this project, build a tree of game states, evaluate those states based off of screen data, and then successfully adapt my bot to succeed in a stochastic environment. Thank you for watching.